Hey everyone, welcome back to another explainer. Today we've got a really fun mission ahead of us. We're going to decode the exact physics that keep our world turning. Literally, we're looking at uniform circular motion. But we aren't just going to stare at a bunch of dry equations today. Nope, we're putting on our hard hats and looking at this whole thing through the eyes of a safety engineer. Okay, let's dive into this. Have you ever looked up at one of those massive Ferris wheels or felt that crushing thrill on a high-speed carnival ride? And wondered what exactly keeps those riders moving safely in a perfect circle instead of just flying straight off into the atmosphere? Well, it's not magic, for sure. It's a beautifully precise blend of physical laws. And today, we're going to challenge you to think exactly like the safety engineers who designed these incredible machines. Here is a quick look at our blueprint for today. First, the amusement park mystery. Then, tangential velocity and acceleration. Third, seeking the center. Fourth, the centripetal force. And finally, radius of curvature. Part 1. The amusement park mystery. Designing the safest ride. So, when you're designing a thrilling but perfectly safe amusement park ride, the real-world stakes are incredibly visceral. You're dealing with human bodies moving at really high speeds. Understanding exactly how those bodies behave when moving in a circle is absolutely crucial. It's the literal foundation of your job. And the core concept here is deceptively simple: uniform circular motion. This happens when a particle, or say our carnival rider, moves in a circle with a constant speed. Now, notice I said constant speed, not constant velocity. Even though the speedometer on the ride might be pegged at a steady number, there is a whole lot of dynamic physics happening beneath the surface, simply because the direction is continuously changing. Section 2, tangential velocity and acceleration, the path and the pace. That constantly changing direction, it means we need to explore the actual path our moving object takes and how we measure its speed right along the very edge of the curve. Imagine you're swinging a ball on a string and suddenly, snap, the string breaks. The ball doesn't keep curving, right? It flies off in a perfectly straight line. That straight line is the tangent. Tangential velocity is basically the speed measured precisely along the edge of that circular path. Its direction is always aligned with the tangent line of the circle at any given instant. Now, what's really interesting about this is applying it to a real calculation, without letting the math completely overwhelm us, of course. Imagine a rotating wheel inside a machine. We know its angular velocity is 32 radians per second, and its diameter is 30 centimeters. As a safety engineer, to find the tangential velocity, which is how fast that outer edge is actually whipping around, you first have the diameter to get a 15-centimeter radius. Convert that to 0.15 meters, multiply by the 32 radians per second, and boom! You find the edges moving at 4.8 meters per second. It's such a quick, elegant way to translate a spinning motion into a straight-line speed. But what if our ride is speeding up or slowing down? Well, that's where we need to contrast two different types of acceleration. Tangential acceleration acts just like your standard linear acceleration. It operates right along the edge to change how fast you're going. Centripetal acceleration, on the other hand, operates completely independently. It acts inward, and it's purely responsible for changing your direction. And the cool part? They always act perfectly perpendicular to one another. Section 3. Seeking the center. Centripetal acceleration. Building on that crucial contrast, let's shift our focus entirely to that inward pull. Because really, this is the defining characteristic of circular motion. Without it, circles simply wouldn't exist. I absolutely love this etymological anchor from our source materials. The word centripetal is literally derived from two Greek words that mean seeking the center. So if you ever get a bit turned around about which way radial or centripetal acceleration is pointing, just remember the origin of the word. It is perpetually, endlessly seeking the center of the circle. And this brilliantly illustrates how these forces actually affect our biology. Look at the data for a dancer or an ice skater spinning at a blisteringly fast 3 revolutions per second. Our balance is maintained by this endolymph fluid in our inner ears, which sits about 7 centimeters from the axis of our spinning head. The radial acceleration actually displaces this fluid, causing that crazy, visceral sensation of dizziness. It's a perfect example of physics directly messing with human biology. All right, let's scale things back up from the inner ear to our amusement park. Imagine passengers on a carnival ride making a horizontal circle with a 5.0-meter radius, and they're completing that giant circle in exactly 4.0 seconds. If you run the math on that velocity and radius, you get a radial acceleration of over 12 meters per second squared. Honestly, that's literally more than the downward force of gravity. It creates those immense chest-compressing forces that make the ride so thrilling in the first place, all while the safety engineer ensures the whole structure remains perfectly sound. Section 4. The centripetal force, the cause of the curve. Okay, so acceleration is just a change in motion, but what actually causes this center-seeking acceleration? Well, here's the absolute key point. Centripetal force isn't some new mysterious magic force. It is simply the total net force acting on an object in uniform circular motion. So whether it's the tension of a chain on a swing ride, the friction of tires on a gripping road, or even gravity holding a satellite in orbit, this net inward force is the true hero keeping our vehicles and rides safely on their circular tracks. Let's look at a super practical safety engineer problem. Imagine a 450-kilogram Jeep taking a sharp turn on a road with a 330-meter radius going at a speed of 20 meters per second. By squaring the speed, multiplying it by the mass, and dividing by the radius, we can figure out the exact centripetal force required to make that turn. It comes out to about 545 newtons. Here's the kicker. If the friction between the tires and the road can't provide that exact amount of force, that Jeep is not making the curve. It's going to slide out. This is exactly why road design and speed limits are so deeply tied to physics. Let's move to our final section and see how this builds. Radius of curvature, changing the curve. So let's look at how this builds into even more complex scenarios. Because in the real world, like on winding mountain roads or those crazy, intricate roller coaster tracks, paths are rarely perfect, continuous circles. Instead, we use what's called the radius of curvature. Think of it like this. It's the radius of an approximate circle drawn at any one specific instantaneous point along a path. It basically acts as the length of the curvature vector. So as the object moves along an uneven curve, this radius dynamically changes, meaning the required centripetal force is constantly shifting. It's like a giant puzzle. To tie all this math together into a really dramatic, real-world application, check out this giant number, 9,000 newtons. According to our data, this is the minimum lift force required for a 900-kilogram helicopter traveling at an impressive 110 meters per second. By plugging these numbers back into our centripetal force equation, an aviation engineer can calculate the exact maximum radius of curvature that helicopter can safely bank through without losing altitude. I mean, that is high-stakes physics playing out right there in the sky. So after decoding tangential velocities, center-seeking accelerations, and the sheer forces that bind them all together, I just have one question to leave you with. Will you look at your next drive around a curved mountain road or your next trip to an amusement park through the eyes of a safety engineer? The hidden architecture of motion is everywhere around us, just waiting to be calculated. Keep analyzing, keep learning, and I'll catch you in our next explainer.